Hello guys. Good morning. Good morning to all of you and welcome to another session. Today we are starting particle physics. So as you know, we have already completed our mathematical physics subject. Now next we are going to complete two of the smallest subjects as particle physics, and then we'll go for the nuclear physics. And after that we can take a big subject like quantum mechanics. So I think there is a problem. Is the audio just hold on a moment. Good morning, Murli Ajay. Where is Harry today? Good morning, Murli Ajay. Where is Harry today? Okay, now I think everything is all right. Let me know once everything is all right. It seems to be okay from my side. Can you also see me clearly and hear me properly? Murli Ajay, is there any background noise yet? Previously background noise was coming. So today this part 1 of particle physics we will be discussing. So without any further ado, let's start. Everything all right now, Harry? No background noise? Okay. Let's start with interaction and particles. You see, there exist four fundamental interactions, namely strong interaction, electromagnetic, weak, and gravitational. These four interactions are there which are accountable for all the physical processes which happens in the whole universe. Are apparently enough to account for all the physical processes and structures in the universe on all scales of size, from atoms to nuclei to galaxies of stars. So it is clearly talking about the strong interaction which we see inside the nucleus. Two galaxies of stars means it is talking about the gravitational interactions. The list of fundamental interaction had changed over the years. Long ago, previously, strong and weak, these two interactions, strong and weak interactions, these two interactions were unknown. Okay, and it was not even clear that gravity that pulls things down to the earth, which we might call terrestrial gravity, is the same as the gravity that pulls the planet to the orbit around the sun. So previously in the early maybe 17th century or 16th century, it was not known that the apple which is falling to the ground because of the kind of gravity, the same gravity is acting between the planets or between the satellites, between the stars. Later on it got clear. One of the Newton's great accomplishment was to show that both terrestrial and astronomical gravity are the same. Okay, so this was given in Newton's law of gravitation. F is equals to g into m1 m2 by r square. Another notable unification was made by Maxwell. This was a very significant advancement or development done by Maxwell. He demonstrated that electric and magnetic forces can be traced to a single interaction between charged particles that was named as electromagnetic interaction. Okay, and you know Maxwell gave four relations regarding the electrodynamics, and there you see that changing electric field induces magnetic field and changing magnetic field also induces electric field. So he basically unified this electric and magnetic nature of two forces. So they are interconvertible. Okay. So mainly four interactions we need to know. Strong interaction we see inside the nucleus. Electromagnetic interaction we see generally between charged particles. Weak interaction, whenever we observe any decay, weak interaction comes into play. And gravitational, this affects all the particles. So from the small object also gravitational interaction acts, but that magnitude is very small, that is why it is not significantly observable. It becomes significant in case of heavier masses like planets, then stars. Now we need to quantify these four interactions. So four fundamental interaction, as you can see, the strong force appears inside the nucleus. This is responsible for binding the nucleus of an atom. Then if I talk about electromagnetic force, you see electromagnetic force, nucleus is positive and the electrons are negative, so an electromagnetic attraction is acting between the negatively charged particle and the positively charged particle. So this accounts the holding of electrons in place, otherwise the electron would have been displaced. Weak force, this is responsible for the decay. Whenever you see radioactive atoms, so it spontaneously decay, so that decay is governed by the weak force. You see in this picture, gravity holds galaxies together. Four fundamental interaction: strong, electromagnetic, weak and gravitational. So the same thing has been told. So you can keep this picture in mind to differentiate between different interactions: strong, electromagnetic, weak and gravitational. Now in a table we will try to understand the basic features. This PDF I will share in the course folder, so you don't need to write much. So you see interaction, particle affected, range, relative strength, characteristic time, particle exchange, role in universe. So this one we are doing from Arthur Baeser. Okay, in Arthur Baeser book, the particle physics has been given in a very good way, in short. So although we'll discuss everything in the class, but if you are interested, you can go through this one particular chapter from Arthur Baeser. So strong interaction, what are the particles which gets affected? Quarks and hadrons. Quarks, you know, the constituent of nucleons, constituents of nucleons. Nucleons means both proton or neutron, and hadrons. So the range is basically 10 to the power minus 15 meter, very small, 1 Fermi, actually this is 1 femtometer. Relative strength is 1, so we are representing the other fundamental interaction strength in terms of the strong. So let's take strong interaction is 1. So this is the strongest force, strongest interaction. Characteristic time 10 to the power minus 23 second. So it is like the time it takes to occur the interaction. Okay, no? That is 10 to the power minus 23 second. For an example, let's say if I keep a charged particle here, charged particle. Now if you consider a point where you want to find its interaction, so the time it takes to happen, to occur this effect, that is the characteristic time. You see how small it is, 10 to the power minus 23 second. Particle exchange, gluons. Role in universe, holds quark together to form nucleons. For hadrons, particle exchange is meson. We will talk about this hadrons meson later in this class only. This is responsible for holding nucleons together to form atomic nuclei. So you know, inside the nucleus we have nucleons, proton and neutron, and inside the proton we have quark structure like this. So this gluon exchange, this holds the quarks together. This is done due to the strong interaction, and this proton neutron individually, they are also bounded by this strong interaction. Understood? It's a simple thing. Next, talk about electromagnetic. It affects all the charged particle, and you know, if you place a charged particle, its influence extends over to infinity in all direction, right? So its range is infinity, but as you can see, for a strong interaction the range is finite, so it acts only for 10 to the minus 15 meter. Beyond that, there is no effect of a strong interaction. But for electromagnetic interaction, it extends up to infinity, and the strength is, it is 1 by 100 time. So you can see it is weaker as compared to strong interaction, and the time it takes 10 to the minus 20 seconds. So you need to remember the order. Here 10 to the minus 23 second, here 10 to the power minus 20 second, and the particle exchange is photons, determine structure of atoms, solids, liquid, important factor in astronomical universe. So here these three things are mainly important. One is range, then relative strength, and characteristic time. And look, whenever in an interaction you see photons, gamma, whenever in an interaction you see gamma, you will understand that it is being carried out by electromagnetic interaction. Okay, this is a cheat code you can use. For weak, it affects quarks and leptons. Range is 10 to the power minus 18 meter, okay, inside the nucleus. The relative strength is 1 by 10 to the power 5. So you can see it is very small. It is like 1000 times smaller than the electromagnetic interaction. And the characteristic time, you need to remember here, 10 to the power minus 10 second. It is the tau value. Characteristic time is represented by tau. 10 to the minus 23, 10 to the minus 20, then 10 to the minus 10, and it affects intermediate bosons. It basically mediates transformation of quarks, leptons, helps determine composition of atomic nuclei. And gravitational, it affects all the particles. Its range is also infinity as the electromagnetic interaction, and you can see it is very weak. You see, it is 1000 times lesser than electromagnetic, and electromagnetic is 100 times lesser than the strong. But gravitational, you can imagine, it is like weakest, 10 to the power 5 into 10 to the power 34. So 10 to 1 by 10 to the power 34 times lesser than weak. And the characteristic time, you can say 10 to the power 16. Graviton, not experimentally detected, assemble matter into planets, stars and galaxies. Okay. The main important thing in here, the characteristic time, 10 to the minus 23 for strong, 10 to the power minus 20. So 3 order change for electromagnetic, 10 to the power minus 10 for weak, and 10 to the power 16 for gravitational. Now solve this problem. A relativistic particle of travels a length of 3 into 10 to the minus 3 meter in air before decay. Then decay starts. The decay process of the particle is dominated by relativistic particle, means we can take the speed is equals to c. Can you do this? What will be the answer? Strong, electromagnetic, weak or gravitational? You see here what is happening, the traveling distance d is 3 into 10 to the power minus 3 meter. V is equals to 3 into 10 to the power 8 meter per second. So the time it takes to travel this distance before decay is equals to d by v. So 3 into 10 to the power minus 3 divided by 3 into 10 to the power 8 second. So this is 10 to the power minus 11 second. And as you can see, the order of characteristic time, it is 10 to the minus 10 second per week. And you see for other it is not nearby. So it is, this is approximate order. It will varies a little bit for various particles. So 10 to the minus 11 second, from this we can conclude that this is the decay process of the particle is dominated by weak interactions. Okay. Yes, Ajay. Now can you do this problem? The mean lifetime of the following decays, like rho naught is converting into pi plus pi minus, pi 0 gamma plus gamma, mu minus electron electron antineutrino muon neutrino, tau rho tau pi tau mu respectively. They satisfy. Mean lifetime is, it is talking about the characteristic time. Here we can see gamma. So obviously this will be your electromagnetic interaction, right? And here mu1 is a lepton, decay of lepton. So obviously this will be weak interaction, and this will become strong interaction. Now tell me which of the option will be correct. C. Rho naught is getting converted into pi plus plus pi minus. So this is a strong interaction. With tau rho is equals to approximately 10 to the power minus 23 second. Next, pi 0 is converting into 2 gamma. This is an electromagnetic interaction. Tau pi 10 to the power minus 20 second mu minus e minus nu e bar nu mu, this is and weak interaction tau mu approximately 10 to the power minus 10 second. So you see which one is greater? Tau mu is greatest, least is tau rho, bigger than that it is tau pi, bigger than that tau mu. So this is given in option C. Okay, now let's talk about the most important slide. Let me take you to the most important slide of this particle physics topic. So this table you must remember: classification of elementary particle. You can also write if you want, so it will be one time practice also. Classification of elementary particles. Elementary particles are primarily classified as per their spin. Integral spin means bosons, or half-word integral spins. Like this 0 will not be there, so by mistake we have written 0 here. Half, 3 by 2, 5 by 2 and so on, half-odd integers. Those are fermions. In bosons category we have photons whose spin is spin 1. Photon is a spin 1 particle. This information will be utilized many times. Photon spin 1, graviton spin 2, pions, pi mesons actually. It has 3 members: pi plus, pi 0, pi meson, pi minus. Chions means chi mesons and eta 0 mesons. Chions has 4 members: K plus, K minus, K0, K0 bar. Then in the fermion family we have leptons. So 6 leptons are there: electron, muon, tyon and their neutrino. Electron, neutrino, muon, neutrino, tyon, neutrino. If you see a bar above them, so it becomes electron antineutrino, muon antineutrino, tyon antineutrino. For baryons, they are classified into nucleons. Baryons means nucleons or baryons. Inside nucleons we have proton and neutron. Sigma hyperons, sigma plus minus 0. Sigma hyperon is also baryons. Lambda hyperon, lambda naught, lambda 0. Cascade, these are called cascade. Cascade minus, cascade 0, cascade hyperon, and finally omega hyperon. So you can remember it in this way. Let me know once it is done. This classification you must remember. You see, these hadrons are classified into baryons and mesons. So baryons and mesons, they are collectively known as hadrons. Leptons are lighter particle like electron, muon, tyon. So they have less mass as compared to baryons and mesons. Baryons and mesons are heavy mass, so they are called hadrons. And what is the fundamental difference between them? Baryons, they composed of 3 quarks, and mesons, they are composed of 2 quarks. Actually 1 quark and 1 anti-quark. So quark model we will discuss later, but for the time being you know this particular difference. Is it done, guys? Okay. Now whenever we will talking about the quantum number, lepton quantum number, baryon quantum number, we will discuss. So if some particle is a member of lepton, so lepton number will be +1. For electron, muon, tyon, electron, neutrino, muon, neutrino, tyon, neutron, lepton number will be +1. Now there are 3 types of lepton numbers: electron lepton number, muon lepton number, and tyon lepton number. If it is an electron and electron neutrino, the lepton number will be +1. Okay, and if the antiparticles like positron and electron antineutrino, the electron lepton number will be -1. And for muon, tyon, muon neutrino, tyon neutrino, what will be electron lepton number? 0. If it is not electron or electron neutrino, the lepton number will be 0. Similarly, muon lepton number, it is 1 for muon and muon neutrino. It is -1 for mu plus, mu bar, and it is 0 for electron, tyon, electron neutrino, tyon neutrino. Same goes for L tau, tyon lepton number. It is +1 for tau minus, nu tau, and it is -1 for tau plus, nu tau bar, and it is 0 for electron, muon. So are you getting the point? For baryon number also, baryon quantum number is defined. If it is a baryon, means whatever things are written here, if we consider those particles, then baryon number will be +1. If they are antiparticle, the baryon number will be -1. If it is not baryon, then baryon number will be 0. So what is the baryon number of electron? 0. What is the baryon number of proton? 1. What is the baryon number of antiproton? -1. Understood this point? So lepton number and baryon number, you need to remember what it is. So to get that, we need to remember what are the members of leptons: electron, muon, tau. 3 particles. You just remember these 3: electron, muon, tau, and their neutrino that compose leptons. Okay. And here proton, neutron, sigma hyperons, lambda, cascade, omega. प्रोटॉन, न्यूट्रॉन, लैम्डा, सिग्मा, कैस्केड, ओमेगा. बस चलिए आगे बढ़ते हैं. सो देयर आर 2 टाइप्स ऑफ कंजर्वेशन लॉज: एग्जैक्ट कंजर्वेशन लॉज and approximate conservation laws. So exact conservation law, what is first of all conservation law is? It states that a particular measurable property of an isolated physical system does not change as the system evolves over time. So one very important quantity, you know, energy. Energy remains conserved. Okay. Exact conservation law includes conservation of mass, energy. Mass can either be created or destroyed. It is like it is just transformed from one form to another. Conservation of linear momentum, conservation of angular momentum, conservation of electric charge. So if you deeply think, nothing in this universe is completely destroyed. If you, let's say, light up a thing, so that thing is just mixing up with the environment, with the atmosphere. You are not able to destroy it. Whatever things present from the early universe till now, everything is present in the universe only. It is just changing its form. Like when we will die, our remains will get converted into something, but it is not destroyed, right? So it is like that. If you deeply think, you get it. And this is exact conservation law. So this exact conservation law is applicable to all types of interaction, all type of reaction. Whatever reaction you consider, these laws will be definitely get conserved. But there are approximate conservation laws which applies to quantities like parity, lepton number, baryon number, strength, hypercharge. These quantities are conserved in certain classes of physical processes, but not in all. So the main difference, if I classify, exact conservation laws are valid for all the type of reactions, and approximate, it is not valid for all the type of reaction, it is valid for certain classes of reaction. Understood the difference between exact and approximate conservation laws? So very simple thing. Let's now go for isospin or isotopic spin. A quantum number associated with the strong interaction symmetry of nucleons, proton and neutrons and other hadrons. It is a concept reflecting the similarity in the behavior of this particle under the strong nuclear force despite their difference in charge. For an example, if you consider the pi family, it has pi plus, pi 0, pi minus. So these particles hardly differ by their masses. Their masses, they are hardly differ by their masses. What does it mean? Their masses are almost equal. they are different by their charges differing from each other by unit charge. So you can consider here charge, it is neutral. The charge of pi plus is plus e, charge of pi minus is minus e. So they are basically differ by unit charge, e plus, 0, e minus. Now if you consider nucleons also, in nucleons we have proton, we have neutron. Proton has charge plus e, neutron has charge 0 e. So they are differ by only one unit charge. Proton and neutron, their mass is also similar. Okay, very similar. Mass of proton similar to mass of neutron. So their masses are differing hardly, but their charge is differing by 1 unit. So to isolate or to specify this type of thing, so these are like isotopes. Okay, these are like isotopes. So as you can consider, as you have seen for the case of electrons, we have seen space quantization, right? Space quantization by taking up the concept of spin. For electron like particle, we have seen the concept of space quantization. So here similarly concept of isospin is introduced, and similar to the space quantization, isospin has also have components. Isospin I and its component I3. The way you have seen that this angular momentum, space quantization basically results from the spin orbit interaction, right? And we have seen that root over L into L plus 1 h cut, that thing happens. So here also similar thing happens. I is equals to isospin, you can see root over I into I plus 1 h cut. In this way it happens. So the magnitude of I is root over I into I plus 1. So that is why the name, it is isospin. So it is not like spin, but it is similar in behavior. By noticing the pattern of spin, this name has been kept, isospin. Do you understand this? I is dimensionless. So you should not write h cut as I is dimensionless. The way you define the component of L along z axis as Lz, here also the component of I along z axis is given by I3, and this I3 can take any values between plus I to minus I. So this is the concept of isospin. Understood? Now the next thing, it is multiplate number. Multiplate number is this: how many members are there in a particular triplet or things like nucleons. Here see for pion, it has 3 charge states: pi plus, pi 0, pi minus. So its multiplate number will be 3. Here for nucleons, it has two charge states, proton, neutron. So its multiplate number will be 2. Okay. So multiplate number is the number of different charge states. Plus I, minus I for third component. No, all the values between plus I and minus I are the values of I3. Look, for LZ, how many values you get? M number of values you get, M H cut, M number of value, and M is between plus minus L. In the same way, your I3 plus minus I. Okay. Clear, Murli? Let's now talk about multiplate number. It is denoted by M. It is defined as the number of different charge states for particles like nucleons, and triplets like pions, and so on. So for nucleons, M is equals to 2. For pions, M is equals to 3. For 2 cations, M is equals to 2. For 2 antications, M is equals to 2. And if there is one member, the way we consider neutral, let's say theta 0, so there is only one component, one member, so M will be equals to 1. Now you see, if I take the example of pions, it has 3 members, pi plus, pi 0, and pi minus. Now we need to associate I3 values for them. So there exists a relationship between this M and I. M is equals to 2I plus 1. Muons will not come into picture here. Muons is only one, mu minus. You see, I is equals to m minus 1 by 2. So you see, for pion, m is equals to 3, so I is equals to 3 minus 1 by 2, that is 1. So you see, I3 will vary from minus I to plus I. Okay, so if you take minus 1, next will be 0, differing by unity. So I3 for plus pi plus is assigned as plus 1, for pi 0 is 0, for pi minus it is assigned as minus 1. Clear? You take the case of nucleons. M is equals to 2, I is equals to 2 minus 1 by 2, so that is half. I3 will come minus I to plus I. So if I take minus half, what will be plus 1? Plus 1, so it becomes plus half. So two things we have: proton. So positive charged particle will be assigned with plus I3. So here what will be the value of I3? It is plus half. For neutron it is minus half. Clear? Let's move on. Let's go to a concept of hypercharge. What is hypercharge? Double of the average charge. Double of the average charge, Q average, of the multiplate. So hypercharge is denoted by Y. So multiplate here, nucleon is a multiplate, pion are multiplate, kaons are multiplates, is like that. double of the average charge of the multiplate. So y is equals to double of the average charge. So from here average charge is equals to y by, okay. Later we will see, later for the time being you just write this formula will come in Gell-Mann-Nisijima formula. Q is equals to I3 plus y by 2. This is a very important relation which we will talk about later also. For the time being you just note it down. Let's take an example. So remember this one, y is equals to 2 times the average charge, hypercharge. If I take an example, let's say 2 protons we have, it is being converted into lambda 0 plus k0 plus p plus phi 0, phi plus, let's say. So can you write the hypercharge value? Just respond quickly. What will be the hypercharge for proton? It is 2 times average charge. Now for proton, the corresponding multiplate is nucleon. We have proton as well as neutron. Charge of proton is plus E, neutron charge is 0, average, okay, E by 2, 2 times average, so 2 times, so it is E, so hypercharge will be 1. Is it understood? For this proton also hypercharge will be 1. Lambda naught is only one thing with 0 charge. So 0, 2 times 0 is again 0. So this will be 0. K0, for this, what will be the value? So you can imagine the multipliers k0, k plus. So again 0 plus E by 2, E by 2. So here it will be again 1. For proton it is 1. What about pi plus? So it is corresponding to pi family. Pi plus, pi 0, pi minus. What is the average charge? It is plus E 0 minus E divided by 3. So it is 0. So this will be 0. And as you can see, average charge is conserved. Is it understood? Tell me. This is a very important concept actually. Concept of hypercharge. One thing you remember, for the kaons, K0, K plus, this is the kaons, and K0 bar, K minus, this is anti-kaons family. Yeah, Murli, that is why I am telling you. We wrote na kaons and anti-kaons. 2 kaons These are two kaons, these are two, this is anti-kaon family. So for this the hypercharge will be -1 for K0 bar. Clear Murli now? Harry, is it clear now? Any more question? K0 is neutral. Okay, K0 bar is neutral, K minus is minus E. K0 and K0 bar, they are neutral particles. K plus has charge plus E, K minus has charge minus E. So if you calculate the average charge for, let's say, K minus or K0 plus, so it is 0 minus E by 2. So this is your Q average. 2 times of Q average will be minus E. So then if instead of K0 if it had K0 bar, we would have written -1. Is it clear now, Murli, Harry? Now there is a very important concept called strangeness number. Hypercharge is a quantum number. Next, strangeness quantum number. It is denoted by S. So for the time being, see, it is defined as the difference between the hypercharge Y and the baryon number B. So strangeness S is equals to Y minus B. This is the formula. So from here Y is equals to S plus B. So as I told you, Q is equals to I3 plus Y by 2. So Q becomes I3 plus B plus S by 2. This is known as Gell-Mann-Nisijima formula. Now whatever particle contain this strangeness, this is a quark actually, strange quark. If strange quark presents, then strangeness number is +1. If strange quark does not present, then strangeness number will be 0. Now what are the strange particles? Strange particles are the particles which contain the strange quarks. Now in the next slide I will be giving you the list of strange particles. Is it done? Look, ions K plus, K0, K minus, K0 bar, and hyperons. So in hyperons we have lambda hyperons, sigma hyperons, cascade, omega. So ions and hyperons are called strange particles. They only contain the strange quarks. Now their strangeness number or strangeness is different. So if I consider the ions family, okay, K plus, it has a strangeness +1. K0, it has a strangeness +1. K minus, it has a strangeness -1, and K0 bar, it has a strangeness -1. So here we are writing the same thing for hyperons. Lambda hyperon, lambda naught, it has strangeness -1. Sigma hyperons, either it is plus, minus, or 0, they all have strangeness -1. Cascade, it is represented by chi or Ji. Cascade 0, it is -2. Cascade minus, it is -2. Omega minus, it is minus. The sign depends upon particle and antiparticle plus minus. Look, if you have S, okay, if there is S, the strangeness will be -1. If you have S bar, it will be +1. Okay, so for this, let's say omega naught, omega minus, it consists of 3s, 3 quarks. So that is why -1 -1 -1, you get -3. Is it clear? So give me a moment. Look, the total strangeness. One more example, sigma plus, let's say sigma plus, it has the content US. So up quark, we'll talk about that. Up quark corresponding strangeness is 0, up quark corresponding strangeness is 0, strange quark corresponding strangeness is -1, so it is -1. Okay, if I take, let's say, cascade 0, its constituent is USS. Okay, so for U, strangeness is 0, strange quark -1, another strange quark -1, so that is why it is -2. If you take, let's say, cascade minus, we'll talk about this, how this USS and all those things will come when we'll talk about the quark model, then you can easily understand. Sigma minus, for this it is DSS. For down quark, strangeness is 0, for strange quark it is -1, for this strange quark it is -1, so you get -2. Okay, one example for this K plus, let's say K plus, it has the content US bar. Okay, so U is 0, S bar is +1, so it is +1. Look, kaons and pions, as I have already mentioned you, if you have noticed it or realized it, just realize, you already know, just realize, I have told you mesons like pi mesons or pions, K mesons or kaons, they consist of 2 quarks, one quark, another anti-quark. So the one example I have given you, K plus. K plus, as I told you, one quark is U, another anti-quark US bar. Okay, now, so let's say if I take pi plus, one quark, another anti-quark. So if pions are not strange particle, as you can see, if I take the example of pions, pi plus, it has a constituent of UD bar. So here strangeness is 0, down is not strange, so it is 0. So that is why strangeness is 0. So for particles whose strangeness, which are not strange particle, their total strangeness number will come out to be 0. I think everything is all right now. Anyone has any question regarding this? Let me know if anyone has any question. Let's move on. Parity. Parity, what is parity? A quantum number associated with the symmetry of physical processes under spatial inversion. Spatial inversion, this one you notice. Spatial inversion. It indicates whether the wave function of a physical system remains unchanged, even parity, or changes, odd parity. Spatial inversion, you see, psi of x, y, z, if you make minus x, minus y, minus z, so this is the parity transformation. So whatever spatial coordinates you have, change it to negative. If we have previously x, y, z, change it to negative, minus x, minus y, minus z. This is a parity transformation. For even parity, the wave function remains the same after under the inversion. So if you make minus x, minus y, minus z, it becomes psi of x, y, z. Similar. For odd parity, parity is minus 1. Okay, parity is minus 1 means there will be a negative sign. If you take minus x, minus y, minus z, it becomes minus of psi x, y, z. So this is the concept of even parity and odd parity. Simple thing, there is nothing like this. Now in the year 2024, a problem came. So to understand that problem, we need to understand like the total parity conservation. One is this spatial parity, another thing is there. So two types of parity we will consider. So first of all, let's talk about conservation of parity. In many physical processes, particularly those involving the strong and electromagnetic interaction, parity is conserved. Parity is conserved in case of strong and electromagnetic, but parity is not conserved in case of weak interaction. Conserved means what? Parity of the initial state is equal to parity of the final state. Let's say you have a reaction A plus B, it is converting into C plus D. So initial state means parity of the reactants should be equals to parity of the product. This is called product, this is called reactants. So parity conservation means parity of the reactants is equal to parity of the product, and this happens in case of strong and electromagnetic. It doesn't happen for weak. Gravitational we do not consider generally, it is involving astronomical objects generally. So mainly three interaction we deal with in particle physics: strong, electromagnetic, and weak. Weak interaction is generally involves a decay. Whenever you see decay, most of the cases it is governed by weak interaction. In nuclear reaction and decays mediated by strong and electromagnetic forces, the parity before and after the interaction remains the same. Parity violation, this is observed in case of beta decay. In weak interaction, parity is not conserved. As I have told you, weak interaction does not hold parity conservation. So this parity violation was first demonstrated by this scientist Qin Xing Wu in 1956. Involving the beta decay. As you know, in case of beta decay, parity violation is observed. So beta decay of cobalt 60, this scientist made an experiment on the beta decay of cobalt 60 and he found the parity violation. The parity is not conserved. The discovery of parity violation in weak interaction showed that the nature does not always behave symmetrically under spatial inversion. Like in the case of, you see, psi minus x minus y minus z, you get this. You may not get it like that. So parity may be violated. Now the problem which came in June 2024, we need to know about few concepts. Okay, first let me tell you, parity associated with orbital angular momentum is minus 1 to the power L. This one you know. If L is equals to 0, parity is even, minus 1 to the power 0 is plus 1. If L is equals to 1 for p orbital, parity is minus 1 to the power 1, that is minus 1. So this thing is pretty simple, nothing is there. Now look, whenever we talk about parity, total parity consists of two things: intrinsic parity and orbital angular momentum parity. So intrinsic parity is the fundamental property of particle that indicates how their quantum state transform under spatial inversion. So whatever we talked about spatial inversion, that is actually the intrinsic parity. So we check whether by changing the sign of the spatial coordinates the wave function changes or not. So each particle has a specific intrinsic parity value. Typically it is plus 1 or minus 1. Okay. Now when two particles interact, their relative motion can be described by orbital angular momentum L, and corresponding to that orbital parity will be there. Orbital parity contribution is minus 1 to the power L. So whenever you see a reaction, this orbital angular momentum will be mentioned and the corresponding parity will be minus 1 to the power L. For S wave, the orbital angular momentum parity will be minus 1 to the power 0. It is 0. For P wave, it is L is equals to 1. So minus 1 to the power 0 is equals to plus 1. And when it is minus 1 to the power 1, it is minus 1. So this becomes even, this becomes odd. Total parity, it is the product of intrinsic parity involved in the particles multiply the orbital parity relative to their relative motion. So total parity before a reaction must be equal to the total parity after the reaction. So you simply remember, total parity equals to intrinsic parities of the involved particles multiplied by the orbital parity related to their relative motion. So if you have A plus B is equals to C plus D, okay, then parity before, if I intrinsic parity, if we denote by eta, so intrinsic parity of A multiplied by intrinsic parity of B times the relative, because of the relative motion of A and B, will have the orbital angular momentum parity. So this will be the total parity. Okay, now this is the parity initial, and it should be equals to parity final. For parity final, intrinsic parity of C, intrinsic parity of D, and the relative, the orbital angular momentum parity because of the relative motion of C and D, that will be minus 1 to the power L. Understood? So based on this, a question came in 2024, this year. You see, pi minus has spin 0 and negative intrinsic parity. Negative intrinsic parity means eta of pi minus is equals to minus 1. In a reaction, a deuteron in its ground state J equals to 1, parity plus 1. The parity of deuteron is plus 1. Captures a pion in P wave. P means L is equals to 1, right? To produce a pair of neutrons, intrinsic parities are given. Intrinsic parity of neutron is plus 1. The neutron will be produced in a state with, can you do this? Did you understand the question now? Harry, Murli, did you understand the question? We will talk about the solution, but before that we need to understand the question. P shape, na P wave. S P D F. So what is the L value for S wave? It is 0. For P wave it is 1. For D it is 2. For F it is 3. So L value is 1 for P, because you need minus 1 to the power L, right? Minus 1 to the power L. So you see the reaction here. What is the reaction? In a reaction, a deuterium in its ground state captures a pi minus and produces a pair of neutrons. So this is the reaction. So this is like the initial, this is the final. Initial thing, this is the final thing. So initial spin, you see, for deuteron, what is spin? Spin is 1, is J equals to 1. For pion, what is the spin? 0. Total spin, S is equals to 1. Initial orbital angular momentum, for D, L is equals to 0. Pi minus L is equals to 1. Total L is equals to 1. So we can say that what is the value of J initial? L minus S to L plus S. So 1 minus 1 to 1 plus 1. That means it can be 0, 1, 2. Now let's talk about the final spin. For neutron, neutron is a spin half particle. Another neutron, spin half particle. Total spin, it is like, you can consider S1, S2, S1 minus S2 to S1 plus S2. So half plus half, half minus half, so 0 and 1. Total, okay, spin हो गया. So we do not know about the final minus 1 to the power L. So we do not know final that thing. So let us write total initial parity. Total initial parity. What is the total initial parity? Eta of D, eta of pi minus minus 1 to the power L. So what is this eta of D? Eta of D is plus 1. Pi minus has intrinsic parity minus 1, and minus 1 to the power L is 1 here. So this is equals to plus 1. total final parity eta of n, eta of n, 2 neutrons minus 1 to the power L. You see in the question, produce a pair of neutrons, intrinsic parity is +1. So it has intrinsic parity +1, it has intrinsic parity +1, and minus 1 to the power L we do not know. And since total initial parity should be equals to total final parity, we can write that this, you see, +1 is equals to, here it is +1 +1 +1 minus 1 to the power L. So for what value of L this is possible? Obviously L should be equals to 0. For this it is possible. If L equals to 1, then it will become -1, right? So one value we have got, L is equals to 0. Now whenever we consider two neutrons are produced in an antisymmetric state. Singlet state, S is equals to 0. So whenever, because these are fermions, so neutrons are fermions, spin half. So two neutrons can be there in an antisymmetric state. You have, I think you have seen it before also. Spin up, spin down, minus, spin down, spin up. Okay. Or you can also write it in this way. One is up, another one is down, down, up. In this way also. Why singlet? Because see, if one is up, one is down in a state, so S is equals to 0. So singlet state, it's 2S plus 1 is equals to 1. S is equals to 0. If you consider triplet state, it is 2s plus 1 is equals to 3. So s is equals to 0. So which option is correct? Option 4 is correct. L is equals to 0, s is equals to clear. So we are stopping here today. In the next session we'll be continuing from here. We'll be talk about charge conjugation and other conservation laws. So I think 2 more classes are required to cover this particle physics and it will be over. So thank you very much guys for joining this session. I hope you find this session useful, and see you tomorrow at 7:30 once again. Till then, bye bye, take care.